I'm sorry to interrupt. I don't know if you can hear me, but we can't hear any audio over Zoom. I think the presenter needs to unmute.
Can you hear now?
Can you hear now? Hello?
Yeah. Yes, thank you very
Okay,
much.
great. Okay, great. Yeah, and the subpopulation shift can cause severe racial bias. For example, in facial recognition systems, it is much easier in recognizing white men than black women. So these issues have raised a lot of attention when the police in Detroit wrongfully accused a black man by using the information provided such AI systems. In recent large-scale models, such like in the DALE2, which are image generation model, these kinds of models even amplify the gender and racial bias over different occupations. For example, let's take a look of the software developed, and we can see the generated images are mostly white men with glasses. So if we cannot resolve these population shift issues, this will even amplify the stereotypes in the society. Okay, in the subpopulation shift, we care more about the performance on these minorities populations. So most of these samples are actually drawn from the same domain when we only care about the subpopulation shifts. And in the domain shifts, we care about the performance where we train the model on a bunch of training domains, and then we aim to generalize this model to the unseen new domains. So domain shift are widely happens in the real world scenarios. So here I would like to use drug reproposing as an example. So the goal for drug reproposing is that we need to reuse approved drugs to tackle the new virus, for example, in the COVID-19 virus, and we can reuse the remdesivir, which is originally used in combating Ebola, but right now people can use it in combating COVID-19. And to reformulate this drug reproposing as a machine learning problems, basically each virus is associated with one target protein, and we have a bunch of drug candidates. We would like to judge whether one drug candidate is useful or not by doing this drug target interaction activity prediction. So to see whether one drug candidate is useful or not, or is active or not. So for a new protein, so for the new virus, which do not have sufficient examples or even do not have any labeled examples to train a good model. So the most direct way is that we can reuse the trained models from existing proteins and directly apply it on this new protein. However, we can observe this will cause the model performance degradations when we apply it on the auto-distribution proteins. To resolve these issues, we can collect a large amount of data from the new proteins to do some tests on the new protein with drug candidates, but it is quite expensive because we need to arrange some wet labs to do these kinds of things. Okay, so it requires us to design machine learning models that are robust, that can also be generalized to the unseen new proteins. So this is for the domain shifts, so we care more about the performance on the new unseen domains. However, in domain shifts, all of these domains, if we only focus on these, are tackle the same task. So in the task shifts, we focus on the problem where we have a bunch of training tasks. We would like to train a model on these training tasks, and then make this model can be generalized to the unseen new test tasks. So here I would like to use these online education examples to show how task shift happens. So online education is very common in recently, and for example, the Coding in Place platform, which is the introduction to coding course, has already been used in more than 2,000 students. So the key problems behind this online education is how can we automatically generate feedbacks for student submissions. We formulate this as a machine learning problem where the input is student solutions for a specific machine learning questions. And each task here could be treated as different rubric items, and each rubric item is associated with one misconceptions. And basically, we will see that whether one solution is follow or not follow these specific rubric items. So the task shift happens when the instructors constantly propose new questions along with new rubric items. Since we do not know what the next rubric item is, we cannot directly reuse the trained models on inferring new misconception items. But it's still possible that if we want to do that, we can hire some teaching assistant, for example, to do the labeling, but the expert labeling is quite expensive since online education platform has already been used in a lot of students. Okay, up to now, we already mentioned 3 different kinds of shifts and mentioned some real-world applications for each of them. And in the next few slides, I would like to mention my research goal and my research overview. And basically, my research goal is aimed to handle the shifts issues in the machine learning pipeline, and specifically to build machine learning models that are unbiased, widely generalizable, and easily adaptable to real-world scenarios. Specifically, we build unbiased machine learning models that can make it works well over different subpopulations, and to build generalizable machine learning models to be generalized to unseen new domains, and also to make machine learning models more adaptable to the new tasks. Apart from these fundamental machine learning contributions, we also apply these methods on the healthcare, smart cities, and the e-commerce platforms. Okay, here is the outline of my remaining talk. And I will specifically discuss first about the subpopulation shift, which I will mention our methods of selective augmentation and is associated with the ICML paper. Before we dive into the details, let's first recap the subpopulation shift. And in the subpopulation shift, we train the model on the entire population. So this model performs well on average, but we need to care more about performance on these minority populations. To further understand why these models will fail, here I would like to provide a simple task. So this task is for the hair color classification, and which is used here to do the illustration. And we can see this is for the training distribution, and we have 1 minority population is male with blonde hair color. And when we train the model on this training distribution, and these models will make a wrong prediction during the test time when we have another examples from this minority population. Why it happens? Because we can see most males are associated with non-blonde hair color. So when the model trained on training distribution, these models will sparsely associate this male information and the non-blonde hair color. And when it sees a new image with male information, it will say, oh, this is definitely with non-blonde hair color. So we say the sparse correlation happens between the gender and the hair color information. So formally, we will define the sparse correlation in some correlations that hold on the training examples, but not always be reliable. To resolve this issue, our goal here is to build unbiased machine learning models that to cancel out these kinds of sparse correlations. The prior approach achieves this by doing the invariant representation learning, which aim to learn the representations that are invariant to attribute. Basically, let's say this is an objective function for the supervised learning loss, and we can calculate the loss between the predicted values and the labels, and then average it over all training examples. So these kinds of approaches directly introduce the regulations to cancel out such sparse attribute. And let's see how this method works. So we have the data set and we feed it into the models, and we can get the representations which contain the hair color information and the gender information. And then we use these regulations to align the representations over different attributes and try to remove the gender information. So this approach can perform pretty good on the data set with salient sparse correlations, like this syllabi, which use sparse correlations between the hair color and the gender. And we can see this kind of methods can perform pretty good if we evaluate on this worst subpopulation accuracy compared with the standard supervised learning approach. However, for some data set, like this party map, which are the image regression data set, here we use the satellite images to predict its party index. So here the party index is sparsely correlated with the region information. And when we evaluate the performance, we can find that this kind of method even hurts the performance compared with the standard supervised learning.
So this LMA, so your problem is you're recognizing people, or what's the problem?
Oh, we recognize the hair color. So
Hair color.
yeah, the hair color. Yeah, yes. Thank you. Yeah, why these models are easier to fail? And we claim that because it is pretty hard to design a regulations that can work pretty good over different data sets. Sometimes the regulations are very strong, it will limit the model's expressive power. And sometimes the regulation is weak, so it is tough to find attribute invariant information. So instead of focus on these model-centric ways, and we focus on the data-centric ways to directly manipulate the training data, which can lead to our algorithms is called LISA. So LISA is a very simple but effective algorithm. And there are two variants of LISA. And the first variant of LISA is we call it intra-label LISA. In intra-label LISA, we aim to mix examples with the same label but from different attributes. Basically, we have these two images. One is male with brown hair color, and another one is female with brown hair color. And when we do such kind of data mixing, and we can get the mixed images and finally to get its loss. If we will repeatedly doing such kinds of procedure, and we can see we can produce a lot of images and with different gender ratios between male and female. So the same thing across all these images is that they all have brown hair color. So it means that different gender ratios will be associated with the same hair color. So after we train a lot of iterations, these models will ignore the gender information and only focus on using hair color to make a prediction. Okay, so we will also like to mention that such kind of selective augmentation process only happen in training. So the intra-label LISA works pretty good in a lot of applications. And we also found another.
Can you explain what it means that the selective augmentation happens in training?
Oh, the selective augmentation happens in training is like we can sample a bunch of examples. So first we have a batch of examples and we have another batch of examples. So every examples we have the same label with the training examples, but from different attributes. And then we can do the mixing on these examples. And
so the mixing happens at the level of so it looks like there you are mixing the image, but are you really mixing the images like this, or are you mixing at the level of the latent encoding?
Oh, we do both. So this is also have a parameter to decide whether we need to mixing for the representation level or do the input level. Yeah, for text, like it's very hard to mix in two texts. So we do it on the representation level, for example. Okay. Thank you. Yeah, so for the intra-attribute LISA, we aim to mixing examples with different labels, but the same attribute. Basically, we can see there are two images, and one is male with brown hair, and one is male with non-brown hair. And we use one hot vectors to represent the labels, and the first value represents the label of brown hair, and second value represents the label of non-brown hair. And when we do such kind of mixing, we can generate a lot of images with different labels. So, but the same thing here is all of them have the same attribute is male. So it means that the gender information is not the reason for the label change. So similarly, if you still change this model for a lot of iterations, these models will also ignore the gender information.
So there are only two attributes, right? We have only two attributes here and a binary classification.
Oh, no. So we essentially apply it on multiple applications. I just use it as an illustration. So you just have the same to select from the same attribute or to select from the different attributes. So this is the only criteria. Yeah.
And then you mix up, then you look at all possible ways to mix up.
Yes, yes. So you can use cut mix or use like an original mix up. You use like a benefit mix up or different kinds of things. Yeah.
Sorry, can I ask a question regarding like a baseline? I guess if instead of doing mix up, if you just upweighted the minority population, like if you just showed the blonde males more often during the training process, does that give similar effects? No.
I think it's a little bit different from the compared with just upweighting. So essentially, this is kind of like upweighting, but we just want to generate more our goal is to actually cancel out the spurious correlation and to find the invariant informations So what is the like a attribute environment informations. So
I mean,
directly use, yeah.
I understand the method is different. I guess I was wondering, is that like a baseline you compared against, or?
Oh, yes, that's true. Yeah, we compare with upweighting, yeah.
Okay, and that doesn't work as well.
It works well, it can improve the performance, but it's not performance that good in some data sets.
Thank you.
Thank you, yeah, thank you for your question. Okay, yeah, we mentioned two variants of Lisa. In practice, we use a hyperparameter to trade off the intra-label Lisa or intra-attribute Lisa. In most cases, the intra-label Lisa works pretty good compared with the intra-attribute. And sometimes we even found a generalizable version of the intra-label Lisa, which will be mentioned in the next slides. So in the next slide, I would like to mention, so we also extend the Lisa to the regression where it also be treated as a generalizable version of the intra-label Lisa. So basically, our analog solution is we need to mix in the label similar example only. So in the classification, you can treat the label similar as has same label or not have different labels. So in the regression, we mix in the label similar examples. We achieve this instead of doing the random picking two examples to be mixed. We change the probability of finding mixing pairs to be inversely proportional to the distance between two labels. So intuitively, we say the label similar examples have the higher probability to be mixed. Let's see how Lisa performs. So we apply Lisa on the classification problems from the toy data set to real world data set. For example, in this digit prediction, where the digit color is variously correlated with the digit information. And also on the bird classification, we aim to classify the water bird and the land bird, since in this like a bird data set, so water bird always in water and the land bird always in land, we will say that the bird type is variously correlated with the background information. Also on the comment toxicity prediction, where the toxicity of the comment is variously correlated with demographic information. And finally, on this hair color prediction. And we can observe that Lisa can achieve very good performance compared with the strongest invariant learning methods with more than 5% on average improvements. And we also apply it on the regression problems on this party estimation. And we can also observe that Lisa can achieve better performance compared with standard approach. So apart from these empirical results, we also provide some theoretical explanations to understand what happens behind the Lisa and why Lisa can perform better. So we can demonstrate that Lisa essentially mitigates the impact of sparse attribute on learning the parameters. So which can lead to a smaller predictive error compared with standard supervised learning and doing the random mixing without adding any constraint to selectively pick examples.
So I don't get it. So what exactly you say when you're doing regression? What are you regressing?
We regress for the party index for every regions. So we have satellite images and you have the light or different kinds of things from satellite images. And we will use these satellite images to regress the party index, which are the index related to party wealth. So this is a typical, this is the data set from like the geospatial domains. Yeah.
Mm-hmm. So like a satellite images. So you want to classify each pixel or region or something?
For entire images. So we have from one region, for example, in Orlando. So we have the one region and we have the party index related to these regions. So this is estimated by
part index. What is that?
Party index. Yeah.
Oh, okay.
Yes. So one image to one value. Yeah. Yeah.
And but these other one, like there's no regression. Are you doing regression in the text that comment?
Text comment is a classification data set. Yes, this is a class.
This is the only
this is the regulation. We actually have more data set in our paper. So if you're interested in
so now is this basically like imbalanced data set you have that some like minority you have fewer sample and the other one you have more sample?
Yes, this is something like for the imbalanced data set, but we will say that the sparse correlation happens in this imbalance, but some imbalance data set, like in some vision data sets, there are no like sparse correlations or no any kinds of correlations that happens behind this data set. Okay. So So the key takeaways from this part is that we propose Lisa to selectively augment examples and to cancel sparse correlations to find the attribute invariant informations, and which can achieve that unbiased models under the subpopulation shift. So Lisa essentially works pretty good on this WILDS benchmark, which includes the data sets with natural distribution shifts, and Lisa is currently on the top of this overall leaderboard.
So can you speculate a little bit of what, because you kind of jumped through very quickly about the theory. So let's say you have a data set in which every chef is French, and you know, I don't know, every barber is Italian.
Okay.
Right. And this is your training data.
Yes.
You are feeding this to a system. Why do you say that it's incorrect if you are going to show somebody who is a chef and is going to say French? Why is that incorrect?
You mean, maybe I can clarify your question. Yeah. So you mean like why this happens? We have the attribute, why this attribute will sparsely correlated with the label.
Why it's curious? If that's the correlation in your training data, why is that a spurious correlation?
Yeah, this is a good question. Yeah. So we would say that this correlation only happens during training time, but in the test time, we do not think this is correct.
Yeah, but that's your training data, right? That's you cannot imagine that your system is going to pick from the big knowledge of the universe something else which is not in the training data. If that correlation is present in the training data and it's consistent in the training data, what is exactly the theoretical reason for changing it?
I see. So you mean like why these models change the correlations during the test time?
Yeah. What is the justification behind saying that this correlation is valid, this correlation is spurious?
Oh, I see. This is a very good question. So we typically will assume there are a bunch of attributes, and some attributes are very strongly correlated with the labels, but not always hold in this specific test data. If this is not observable, we also apply our methods and to directly mixing examples with the same labels, but without considering this attribute, because we, as you mentioned, we cannot distinguish whether some attribute are sparse attribute or some attribute are the causal attribute. So we just mixing in this kind of method also works well on some data set. But another way is that sometimes people's domain knowledge will say, oh, this is not like very strong correlated with the labels like the bird classification. So you know, water bird always in water and land bird always in land. If you want like to classify the bird types, so you know, like the background information could be treated as sparse correlation because you only needed the bird characteristics to do such kind of classification. And in an extreme case that there are two correlations that are completely correlated with the labels, but only during the test time, we have one correlation happens. We also have another papers to build ensemble models and to distinguish these kinds of correlations. And in the test time, if you can find active ways to do some labeling, you can identify which correlation is real or not real during the test. We have another papers to discuss this.
So if I could tease that out a little bit more.
Okay.
I think the question, and the harder question is there when you how do you identify the spurious ones? Is that something that through analysis is done after you've trained and now you're at test time, you see poor performance in some populations? And is there ways to say automatically detect that, or is this something that you have to have, you know, a great amount of effort to identify these?
I see. There are a bunch of ways to do so. So sometimes you will have something on hand, you will have domain knowledge and to say, oh, this correlation might be sparse correlations, or you have a bunch of attributes. And so this is like you can do some analysis and to see which correlation is possibly to be sparse correlation. If you is not observable, as I mentioned, so you can mix in data with different, do not consider attribute with same labels, so it will produce a lot of different variants and to see which one would be the causal information. And another thing is that you can also train twice. So the first time you train the models, you get the EIM results. And these EIM results, you have a lot of misclassified examples during the test time. So these examples are probably come from the minorities populations, and you can do some pseudo labeling on this attribute and to see whether you can further leverage our method on top of this signal chain. So yeah.
So you go into this process already knowing what you've determined to be.
Yes.
And now you're trying to.
Yes. So there are a bunch of ways to resolve this issue. Yeah.
Maybe I think so that given time to finish the time. You can postpone this. Okay. Yeah.
Okay.
Let's continue.
Okay, sounds good. Thank you. Okay, so we now mentioned this subpopulation shift, and we propose selective augmentation to handle this subpopulation shift. And in the second part, I would like to discuss about domain shifts. And in the domain shifts, we will specifically discuss the structure generation to handle the domain shift issue. And let's first do some comparison between the subpopulation shifts versus domain shifts. And in the subpopulation shifts, we care about the performance on these minority subpopulations. However, all examples are drawn from the same domains if we only consider subpopulation shifts. And in the domain shifts, we care about the performance where we have a bunch of training domains, and we would like to train this model and to make these models generalize well to the unseen new domains. And the problem here is sometimes these methods will even overfit on these training domains and cannot generalize well to unseen new domains. For example, in this drug target in binding affinity activity prediction, so we generalize these models to the unseen new proteins, we can observe the performance degradations. And another example is the land usage prediction. Here we use the satellite images to predict its land use. So we have one image and with one labels is for the land use. So we train a model from a couple of regions, and then we aim to generalize this model to the unseen new regions. And we can also observe the performance degradations on these unseen new regions. So here, our goal is to build the robust machine learning models that can be generalized well to arbitrary unseen new domains. So the prior approach typically learn a single generic models to achieve this goal. So where we have the shared models, the shared models can capture the general information for prediction from training and test domains. However, such kinds of shared models only capture the general information, and which is essentially lack of domain-specific knowledge, which is also very important in making the prediction. So which will finally achieve the suboptimal performance. Instead of focusing on this learning a single generic models, so we can enable to learn the domain-specific models. Basically, we aim to assign every domain has its own model. And such kinds of domain-specific models can capture both general features and domain-specific knowledge, which can finally provide more accurate information. However, there are two challenges to build such kind of domain-specific models. The first challenge here is that there are no data in the test domains, no label data in the test domains. So how can we build domain-specific models in the test domains? And the another challenge is that, so it is very easy to build a single generic models. We can collect all examples and to train these models. However, sometimes the training domains only have limited examples, which are not enough to train its own domain-specific models. And to resolve these two challenges, and we propose D3G, which is a structured generation methods, and we essentially would like to leverage some meta information from the test domains to bridge the gap between training and test domains. So I will first present the overview of D3G and then mention that how D3G can help us resolve these two challenges. So we now have the training data, and every training domain has its own domain-specific function. And when we have a new test domain T, and we aim to leverage these training domain-specific functions to build the test domain-specific functions by leveraging some domain relations. So let's see how D3G can resolve these two challenges. So the first challenge here is that we do not leverage any label data from test domains. And this to resolve it is just by weighting the training domain specific functions. Basically, we have the test domain T, we will feed this data to every training domain specific functions. We would like to leverage the relations between training domain 1 and test domain T to weight these training domain specific functions and to get the function FT. So basically, we need to emphasize the similar training domains. So if we have some metadata from test domains, we will build the relationships. So how to build such kind of relationships? And there are a bunch of ways to build the relationships. We now leverage the domain metadata. So for example, here we have the proteins as the domains, and we have a pair of domain information. And in this drug target interaction activity prediction example, we can first leverage some existing domain relations. For example, we will have the protein-protein interactions. So such kinds of protein-protein interaction can capture the relationship across different proteins. However, in some real-world applications, these kinds of fixed domain relations are not always be reliable. So always be accessible, and may not also reflect the actual information behind the data. So another way is that we can leverage this domain metadata. For example, we here leverage the structure of every protein as domain metadata and feed it into a small neural network. And this neural network can produce the learned relations. And such kind of learned relations can serve as a complementary to the fixed relations and to refine these fixed relations. Since this small neural network will be trained together with the entire predictive model, we will say that this kind of domain relations can fully reflect the information behind the data. And by combining these two kinds of relation sources, and we can get the final domain relation omega ij. And we can use these domain relations to resolve the challenge 1. And in terms of challenge 2, so the training domains only has limited data to train, which are not enough to train a good model. So this resolve it by optimizing all functions for each individual sample loss. So basically, we can see that we have the training domain 1. We will use the data from training domain 1 to optimize its corresponding functions, which is function F1. So using this supervised learning loss. And we also want to use the training domain 1 to optimize other domain-specific functions. But it is unreasonable to use quite irrelevant information to optimize other domain-specific functions. So here we would like to build the domain relations again and to optimize other domain-specific functions. So such kind of domain relations will be used to control the impact of one training domain in optimizing other domain-specific functions. So basically, let's see if the relation between the training domain 1 and 2 is larger than training domain 1 and n. So it means that the training domain 1 has a high impact in optimizing function F2. We achieve this by designing such kinds of consistency loss, which is first doing the inference by doing the weighted inference from other domain-specific functions for one training domain and to make it close to its labels. So by combining these two losses, we can optimize the entire models, and this is how this regime can resolve these two challenges. So in our experiments, we apply this regime on the drug target interaction problem, which is a graph data, and on the land usage prediction, which we need to generate to unseen new regions and use the satellite image data. And we can observe that this regime can achieve better performance compared with best prior methods. To be fair comparison, we also leverage this domain metadata in this, using it in these best prior methods. And we also apply it on the regression problems on this temperature prediction, where we use the time series data and we aim to generate this model from some regions to other regions. And we can also observe this region can reduce predictive error compared with best prior methods. Apart from these empirical results, we also provide some theoretical explanations to show why this regime can achieve better performance. Basically, we have some mild assumptions, and our assumption is to assume that the domain relations is controlled by the difference of the domain representations and also with one bandwidth. So we evaluate access risk of the target domain T, which is bounded by a bias bound and a variance bound. So basically, for the standard models, since we treated all the training domains equally, so it means that we need a larger bandwidth, and which can lead to a larger bias error and small variance error. And when the domain relations can fully capture the domain similarity, so the D3G can find a better bandwidth to trade off the bias and the variance, and to achieve smaller access risk compared with standard approach. Okay, the takeaway here is that we propose D3G to structurally bridge the training and test domains and to make these models more generalizable to the domain shifts. And in this direction, beyond proposing some new algorithms, we also investigate some data set to accelerate the research in the domain shifts, where we investigate the domain shifts over time. Here, time is treated as domains. And we propose wild time, which contains the data sets with a gradual distribution shift over time, including the data set for general image classification, satellite image classification, some healthcare applications, and some text applications. So we also make it a Python package, which is pretty easy to use. Okay, this is for the sixth.
I had a question about your results. So for the domain shift pass, could you go back to your results slide, I guess, there? Yeah, I guess you explained the drug target interaction. How does the domain shift work in, for instance, the land usage?
Okay, this is a good question. So basically, we train a model from a bunch of regions, for example, in some countries, and then we would like to apply this model on the unseen.
So the domain shift is from countries.
Yes.
That in kind of the US, you train kind of this one land usage prediction model.
Yes.
Okay, and then essentially for creating the specialized functions across the different domains, kind of how, I guess I didn't quite understand how that part of the algorithm worked.
You mean for this land usage prediction? Yeah. So how algorithm can apply on this?
Kind of how you're doing this, how you're creating the specialized function.
Relationship.
Oh, the relation. Oh, okay. Okay. So in this one, we leverage the geographic information to determine this, which is motivated by some geographic law from the first law of geography, and where we say that the close regions may have more similarities, but the key problem is that sometimes the close regions do not fully follow the similar things. And so we also use this relationship or descriptions of this domain metadata, so like the region descriptions, to feed into a neural network and to learn the relations, which can calibrate the fixed relations. We also show some case studies in our paper.
So it's like using extra knowledge to bridge the data.
Yes, for the domain metadata. So it can be treated as a metadata adaptation. So
okay.
Yeah.
Thanks.
Okay, thank you. So any other questions? Okay, maybe I can move on. Okay, so in the last part, I would like to discuss about task shifts, and we will specifically discuss how to learn with limited tasks and focus on this iClear paper. And apart from this, like the methodology contributions, here I would also like to briefly mention our applications in smart city, healthcare, and e-commerce. Okay, before we start, let's do some comparison between the task domain shifts to the task shifts. In the domain shifts, we will say that the training domains are different from the test domains, but all of them are specifically focused on the same task. For example, to do the same class classification. And in the task shift, we will say that we aim to train the model from some training tasks and then to adapt this model to the unseen new test tasks. So the training objectives may be semantically different from test objectives. So the problem here is that such kind of trained models from the training tasks cannot be directly deployed to the unseen new test tasks. So to support such kinds of new task learning, because we need to first know what the next task is, so we need to do the adaptation. And in terms of adaptation, so we can collect some examples from the test tasks, and then we use these examples to refresh the trained model and to make it can be works well on this unseen new test task. However, it is pretty hard to collect a large amount of examples. So our goal here is to enable the quick adaptation to adapt the trained model to a new task with only limited labeled examples. So the key point here is that we need to build a very good adaptable model function F, and in the machine learning field, we typically call it as a meta model. So the standard approach to build such kind of meta model is that we can collect a bunch of training tasks. So here, each training task is to classify 3 different objects. And we use these training tasks, use different kinds of meta learning algorithms, and to train a meta model. And then we have the new test task. So this new test task is different from any training tasks. And the training set of this new test task only have limited data points. So we use this training set to refresh this meta model and to get the task-specific models that specified to this new test task. And finally, we evaluate the performance. We have the new test examples to feed into the task-specific model to get the prediction. And this kind of approach works pretty good on the applications, like in the classical image classification. We have a large amount of base classes, and we can construct a large amount of training tasks. And train this model on these training tasks, it can work well and adapt well on the new class classification. However, in some real-world applications, such like in medical image classification, where we only have 20, for example, we have a limited base classes, we can only construct a limited amount of constructed training tasks. And then the model trained on this limited training task cannot adapt well to this new unseen skin disease classification, because it essentially memorizes the adaptation process happens in the training process. To resolve these issues, and we propose MLTI, and the MLTI is a task augmentation method. And here, the task augmentation, our goal is to densify the task distribution. And task augmentation means that we need to generate some new input-output mappings. So to further judge what is a good augmented task, and we propose 2 criteria. And basically our criteria is follows this very simple example. So we have the original task distribution, we have the true task distribution, which is marked in gray, and we have some sample tasks, and we can use these sample tasks to infer the empirical task distribution. And to further judge what is a good augmented tasks, and this is descriptions of the first criteria. And in the first criteria, we should make these augmented tasks to be the task-aware augmentation. So we need to have existing mappings and to generate this augmented mapping. So if these augmented tasks are not follow this first criteria, let's see what will happen. So such kind of augmented tasks will be far away from these sampled tasks. And it will even hurt the inference on this empirical task distribution. And this is not what we expected. And the other criteria is that we should make this constructed or augmented task to provide additional information in inferring the meta model. So mathematically, we will say condition on the existing tasks, we should make these augmented tasks to provide additional information in inferring the meta model, whereas the mutual information is larger than 0. So if this augmented task can follow these 2 criteria, we'll say these augmented tasks can essentially densify the entire distribution and get a better empirical task distribution. To make this more practical, so we will provide a practical solution to augment tasks by generating some class-level input-output mapping. Basically, we have the 2 original tasks, and we can construct the class-level. We have the class-level mappings from these original tasks, from the input to the output. And we would like to make this augment task to generate the new one-to-one mappings. So here, we will make it to augment it from a pair of classes and to be associated with another new classes. and to finally construct such kind of one-to-one mapping. So different from the original settings to classify the different diseases, and we aim to partially to classify the different disease pairs. So let's see how one augmentation works. So basically, we will feed this a part of examples into pre-layers and to get its representations. And we can also make these augmented representations happens in the representation levels, and where there are a bunch of ways we leverage it to doing such kind of augmentation. And we just show a very simple case to do the linear combination. And where the lambda is a random variable sampled from beta distribution. And we will finally feed into post layers and to get its predicted values, which is associated with a new label. And to further judge whether this pipeline follows these two criteria, we'll say because this is based on the original task, so this is task-aware augmentation. And in the settings, since we intuitively introduce some randomness in augmented representations. So this say the augmented task can provide additional information on inferring the meta model. And we can also mathematically prove that this mutual information is larger than 0. Furthermore, we need to notice that MLTI is a meta model agnostic approach, which can be integrated into different kinds of meta learning algorithms. And we further apply our method to the different kinds of data sets, like a skin disease classification, where we need to classify unseen new skin diseases. Also on cell type classification, we use gene data to classify unseen new cell types. Also on general image classification, on few-shot image classification, and finally on this feedback generation example, as I mentioned before. So compared with best prior approach that we in our lab we proposed before, so MLTI can also improve the performance compared with standard approach and best prior methods. And apart from these empirical results, we further provide some theoretical analysis to justify why MLTI can achieve better performance. We can demonstrate that MLTI is essentially impose a regularization, where such kinds of regularizations can reduce the meta model complexity, whereas the meta model complexity is controlled by a parameter gamma. So this gamma values is also reflected in this generalization bound. So where we can see that MLTI can regularize the meta model and achieve smaller gamma and lead to a smaller generalization error compared with the standard approach. So we further illustrate these augmented tasks by mapping each task in two-dimensional space. And we can see the original task is marked in star, and this augmented task is essentially densifies the entire task distribution. Okay, the key takeaway here is that we propose MLTI to improve the adaptability to task shifts by doing the task augmentation, which works pretty good, especially when only training with limited tasks. So in this direction, apart from these methodology contributions, we also collaborate with some domain experts to work on some interdisciplinary applications. For example, we need to do the cross-region geospatial prediction, where we train the model from a bunch of source regions and then apply it on adapt it on these target regions, where in the target regions have quite different patterns from some source regions. And in target regions, we only have limited records. We incorporate some domain knowledge by using some like region functionality, which like us to say that the POI information or different kinds of region informations into the model. And we apply it on the traffic prediction, where we only use 3 days new region data, and our method can achieve more than 5% improvements compared with best prior methods. And we also apply it on the water pH value prediction, where we only use 1 year new region data to get, and our method can get more than 8% improvements. And another application is about the new drug recommendation. Here we aim to recommend the newly approved drugs to the patients, where the newly approved drugs only have limited records. So we leverage the domain knowledge is about the patient phenotypes and the drug ontology to capture the relationships behind the patient and behind the drugs. We apply it on the IQVIA dataset, which include 100K patients. So this dataset including the patient's claims from the IQVIA company. and our method achieved more than 7% improvements. And this is a joint work with some medicine schools like Northwest Medicine, UIUC Medicine, and Stanford Medicine. So apart from these interdisciplinary applications, we also apply our method in the industrial platforms. So we specifically apply it to the Alibaba platforms in the e-commerce platform. And our goal is to predict the number of checkouts for data insufficient categories of products. So we can see in the online A/B test, our methods can improve 3% of the number of orders compared with the product model, which can finally lead to 2.5 million weekly gross merchandise value gains. So besides this industrial impact, our methods also be applied by other people to various applications like dialogue generation, disease classification, and regressions. Also, finally, in summary, so we discussed population shift and proposed Lisa to do the selective augmentation and to build unbiased machine learning models, where we actually do not require a specific information from target scenario. And the domain shift can happen together with the subpopulation shift, but it also has its own scopes. And we propose D3G to structurally bridge the training and test domains and to build generalizable versions. So here we require some domain metadata from target scenarios. And finally, about the task shifts. So task shifts can also happen together with the domain shifts and the subpopulation shifts, but it also have its own problems. And in the task shifts, we propose MLTI to improve adaptivity by doing the task interpolation. So where we require some limited labeled examples from target scenarios to do the adaptation. So it seems like the more the problem it can solve, the more the information will be required from target scenarios. Okay, so this is the overview of this talk. And you may would like to know what the next step is. So in the future, I plan to push my current results towards my long-term research goal is to build reliable and adaptable machine learning systems. And there are a bunch of projects I feel that I'm very interested to do. The first one will happen during the training stage. And in the training stage, I aim to build the reliable training models. So my current works already show that we can devise these machine learning models by doing the selective augmentation. And in the future, I plan to more systematically investigate the problems by mitigating the low quality data impact. So to see that some data points can cause bias and some data points with noise or even some fake data points. And one way to do so is to do some data evaluation to judge the importance of every data points and to filter out the data points that can cause negative impacts. And in terms of training stage, we also seek the support from the community by organizing this ICM 2022 workshop on pre-training. Okay, so the second part is that I aim to do some research in the deployment stage. And in the deployment stage, I aim to do the flexible deployment. And my recent works already show that we can only manipulate a small proportion of the neural network and to make it work well over different kinds of distribution shifts. So sometimes we can manipulate the first blocks, or sometimes we manipulate the last layer. So we do not need to do the 4-layer fine-tuning. We only to manipulate or intervene a small proportion of this neural network. And in the future, I plan to do on the effective instructive adaptation. Basically, we have the models, and we would like to deploy or flexible deploy to different kinds of scenarios. So in these scenarios, every scenarios may have different tasks or different like domains, but it may have some instructions, especially for different tasks. We can provide some instructions. And we hope these models can first reason these kinds of instructions and to well adapt to different kinds of scenarios. And finally, on the last stage, I would like to extend my current work from which mainly focus on static adaptation to the continuous adaptation. We aim to make these machine learning models can constantly adapt to over different scenarios. And my recent works already proposed a benchmark to have some initial results on this wild time benchmark. And in the future, I plan to leverage the power of human and to build the interactive continuous adaptation. And such kind of humans can provide the additional information to help us answer these two questions. When do we need to do the adaptation and how to achieve quicker adaptation? And finally, apart from this, like fundamental machine learning plans, I aim also to do more on interdisciplinary applications. I will specifically focus on the problem like healthcare and medicine, and to solve the three issues in these healthcare problems. One for the limited data, so like doing the rare disease detection. Also, we need to achieve the personalization, the personalized healthcare models, but also protect the patient privacy. And finally, to build the unbiased and fair machine learning models or healthcare platforms. So apart from these healthcare applications, I'm also pretty interested to collaborate with people within the department or across department on the problems like in robotics, in autonomous vehicles, and also in intelligent transportation. Okay, this is all for my talk. Thanks to my PhD advisor, postdoc advisor, all collaborators, and the students I mentored, funding agents support my research and the research institutions that I collaborated with. Okay, that's all. Thanks. Any questions? Okay.
In order to mix up, you need to be aware about the kind of space relationship that is existing or that you want to take care of.
We tried, yes, this is true. So first, but we tried to do not leverage such kinds of sparse attribute or leverage any attribute. We only mixing examples from same label. It can also work well. On the regressions settings, we essentially do not leverage such kinds of sparse attribute. We only mixing the labels and the examples, which can also work pretty good. We found in only a few cases that we need to really leverage the sparse or kind of attribute is that this sparse correlation is super strong. So like this hair color classification examples, like in our data set, this minority subpopulations is a very small proportion, only 1% or less than 1%. So in the entire training distribution. So in these cases, we will leverage some like attribute information. But in other cases, so this works pretty good in a lot of real world applications. We can even simplify the methodologies. Yes, you just add the constraint to do the selective augmentation over different labels in regression, in classification, and over similar labels in regression. Yeah. Okay.
I had one question on that. So you're sort of interpolating between data points in order to build up a larger data set in these subpopulations in that first task. I was curious if you looked at how your efforts towards overcoming bias in a subpopulation impact your effort to allow for domain shifts. So because oftentimes in the real world.
Oh, yes.
So does that LISA technique also promote good generalization in new data sets?
Oh, yeah. This is a pretty good question. So we essentially are doing a lot of works. We apply LISA on the domain shifts. So we have the results on both the poly shifts and domain shifts. And we found LISA can also improve on the domain shifts. I can also mention to you which kinds of data set is domain shifts. And basically on this wild benchmarks, most data sets are domain shifts. So we separate these because of this talk. It's like to be better organized to separate these on the second part of this domain shift to leverage more information to get higher performance. Yeah, but then LISA can do helps on the domain shift problems. Okay.
I actually have a quick question.
Okay.
The same topic actually. So when you're merging the picture you have shown, those two pictures are still under the same classification of blonde, right? But when you merge the image of the blonde hair and the darker hair, at what point do you change the classification label? Or how does the classification work with that process?
Oh, I see. So you may mention, give me 1 second. Mention this one.
Exactly.
Oh, so yeah, we will change the ratios between the first image and the last image. So use the parameter which is sampled from random distribution to control it. Yeah, so the labels will follow the same thing happens in the input. So
what about the middle one? Is that classified as blonde, not blonde?
oh, it's 0.5 probability to be brown or 0.5 probability to be non-brown. Yeah.
Okay, thank you.
So this Lisa name, I have seen some other method called Lisa. So are you guys sure that Lisa is the same?
Oh, yeah. Oh, you mean which is Stanford?
No, just that whether it's unique.
Okay.
So other thing, you had this other method called D3 something.
Oh yeah, D3.
So, but I did not find the third.
Oh, that's a D is for the domains. So we use like yes, we not 3 domains. Yeah, it's pretty interesting. Yeah, we say like the domain, like the domain metadata or like domain relations. So we leverage several Ds in the full name. So we simplify it. Yeah.
Like domain.
Yeah, kind of things like that.
I have a question.
Okay.
So, regarding your first one, which is about the subpopulation shift. When we provide the regularization feedback to the model and we force the model to pay attention to specific subpopulation, yes, the subpopulation accuracy will be increased, but with that hurt the overall. I mean, if you overly emphasize, right? Will that hurt the overall population accuracy?
Yes.
And how could you, balance that?
It depends on your requirements. So it depends on scenarios. So basically you will say, oh, this one scenarios needed to care more about the entire population, entire performance. And one scenarios needed to care more about to make these models more fair. So this will like try to balance it different on the requirements of different scenarios. And you can leverage these requirements and to choose which method you want to use. Yeah, but basically it will slightly hurt the performance. It's true. So we found in some data sets it can even improve the entire performance in 1 or 2 data sets if the spurious correlation is not strong, very strong. So this kind of thing is very strong. So you only have 1% of data set from these minority subpopulations in the entire data set. But if you have maybe 5% or something, that it can also help in the entire performance. Yeah.
And when you talk about the part 3, which is the task shift issue, you mentioned that the task shift method and how to apply to different applications. I saw that you discussed the like urban traffic.
Yeah.
Forecasting from one region to another region. You also mentioned water, particularly more like climate and environment.
Yeah.
So here in those kind of applications, what's the definition of the task shift? It sounds like to me like you're changing the location, but the task is still traffic prediction. Right?
Oh yeah. We will say the task shift happens because like the patterns behind the different locations is quite different. So mathematically, we will say that the probability of the y given x, the py given x changes over different regions. So in these cases, you cannot directly apply the model because the patterns change. You need to have some limited examples to help you to adapt these models. So this is also be treated as one kind of task shifts.
But the tasks are still.
Yes.
My question is about the task adaptation.
Yeah.
Are you considering the forgetting as well as one of the metrics when you're talking about the problems?
Oh yeah, I see. These are the pretty good questions. So in this part, we only looking at the forward transfer. So, but in the continuing scenarios, so we also consider some backward transfer settings. Yeah. Thank you.
Okay, well, thank you. Thank you for the talk.
Okay, thank you. Thank you for helping me. Thank you.